So let's go over three examples that will cover basically everything that we just went over. Start with a simple one. And to do this, remember that we're trying to understand the concept of slope of secant lines for nonlinear functions. When we have linear functions, the slope is a given number and it's constant along the entire graph. So perhaps the simplest nonlinear function we can think of is a quadratic. So let's take s of t equals t squared, and let's ask ourselves, what is the average velocity of s of t over the interval 1, 2, right? Very clear question. So the solution, we just need to appeal to the definition. What is the average velocity? Well, if you recall, is delta f, delta the function, so the variation of the function, in this case is s, so that's why we use delta s over delta t, and this is just the value of s, the total change in s, so s at the point 2 minus s at the point 1 divided by 2 minus 1. And this is just equal to, what is s of t? S of t is a function that to each value x and now t associates t squared. It's squared, so this will be equal to 2 squared minus 1 squared, all that divided by 2 minus 1, or 4 minus 1 divided by 2 minus 1, which will be equal to 3 over 1, which is just equal to 3. Okay, so the conclusion is that the average velocity of s over the interval 1, 2 is 3. So in the graph, this is s of t, and if this is 1 and this is 2, we're computing this is 4, this is 1, so we're computing this slope, so this is delta s, and this over here, it corresponds to delta t. And if we wanted to get the instantaneous velocity, this is not part of the question, but for the instantaneous velocity, we need to compute the limit as delta t approaches 0 of the average velocity Remember that geometrically the instantaneous velocity corresponds to the slope of the tangent line. And in order to do that, to compute this instantaneous velocity, we would actually need to take ever smaller intervals here, which we compute the this quotient, this ratio here of the average velocity. So if we were to blow this up, we were to use a magnifying glass. We'll see points on the line, on this curve, points that are really close to each other. So A, in this case we're standing at 1, and this will be the point 1 plus h. And where h is a really small number, and we're computing delta s over delta t, which in this case is equal to h, and for smaller and smaller values of h. Okay, so just remind again that also the slope of the tangent line is equal to limit h goes to 0 of the slope of the secant line, and this is equal to the limit of h when h goes to 0 of s of t of s of 1 plus h, because we're standing at 1, minus s of 1 divided by h. So here, if we go back to the original problem where we computed the average velocity, h is equal to 2. Remember, this is 1 plus h, so this means h is equal to 1. But if we want to get better approximations of the slope of the tangent line, we better get values of h, and consider values of h that are getting closer and closer to 0. So let's look at the next example where we're actually asked to do this. So we'll first try to compute or get an idea formally of how to proceed when we're asked to find the slope of the secant line of the tangent line or the instantaneous velocity. So let's consider again another quadratic based on the position of a particle at time t is s of t 3 t squared, and we're asked to first compute the average velocity over time interval 4, 5, and then we're asked to estimate the instantaneous velocity at t equals 4. So initially we're asked to find an approximation, a very rough approximation, because here we're moving away from the point by 1 to 4, and then we're considering an endpoint which is 5. So this will give us a very rough approximation of the instantaneous velocity. So if we want better approximations, we need to consider points that are closer and closer to 4. Okay, so let's solve this problem. What is the average velocity? It's delta s over delta t, which will be equal to s of 5 minus s 4 divided by 5 minus 4, which is the change in time, and this is equal to 3 times 5 squared minus 3 times 4 squared, all of that divided by 5 minus 4. Remember, the s of a number corresponds to multiplying multiplying by 3 the number that you have inside the parenthesis to square. So here is 3 times what's inside of s, which is 5 squared, and again s of 4 will be 3 times what's inside, which is 4 squared. This gives us 3. We have a common factor of 3. 5 squared, which is 25, minus 16, all that divided by 5 minus 4, which is 1. So we get 9, 3 times 9 over 1, which gives us 27. So this is the average velocity. So for part B, let's remember to estimate the instantaneous velocity or tangent line slope at a time t0. We compute the average velocity for secant line slope over several intervals t0 comma t1, or we can also use t1 comma t0. We just need to approach the point t0, t0, whether from the right or from the left. And the only condition here is that t1 has to be close, really close to t0, and estimate from these values. Also, this is what we'll do. I mean, we'll do it formally. Once we introduce the concept of limit, we won't have to do this hand waving thing. We'll be able to actually prove that the limit is a given quantity that we suspect. So start computing things over the interval 4, 4.1. Okay. Delta S in this case will be equal to, well, delta S over delta T will be equal to 3. I mean, if we do the same thing as before, 3 times 4.1 squared minus 3 times 4 squared, all that divided by 4.1 minus 4. This will be equal to 4.1, so I mean 3 times 4.1 plus 4 times 4.1 minus 4, all of that divided by 4.1 minus 4. And this, if you use a calculator, we can simplify this and this. Will give us 8.10. So 0.1. In this equality, we have used the fact that x squared minus y squared is equal to, this is 3 times 8.1. X squared minus y squared is x minus y times x plus y. For x equals to 4.1 and y equals 4. So that's why we transform, that's how we transform 4.1 squared minus 4 squared and wrote it as 4.1 plus 4 times 4.1 minus 4. Okay, so now this is first computation. For 4.01, so we just moved by 0.01. Delta S over delta T will be equal to 3 times 4.01 squared minus 3 times 4 squared. All that divided by 4.01 minus 4. If you use a calculator, you'll get this is equal to 3 times 8.01. And then at 3.9, so now we use 1 point from the left, 3.9 and delta S over delta T will be equal to 3 times 4 squared minus 3 times 3.9 squared, all that divided by 4 minus 3.9, which will be equal to 7.9 times 3. And then we have another interval. So at the interval 3.9, 4, you have the delta S over delta T is equal to 3 times 4 squared minus 3 times 3.99 squared, all that divided by 4 minus 3.99, which is equal to 7.99 times 3. So we see here that there's a clear trend. Things are getting closer and closer to 3 times 8. Then we estimate that at t equals 4, as we approach t equals 4, we get 3 times 8, which is 24. So the instantaneous velocity is 24. In fact, I had another example, but I think that this should be enough. For now, we'll go over more problems during our problem solving session. So we just now move on to the section 2.2, where we actually get into what the rigorous definition of the notion of limit is.